I'm just going to do an intro. Good morning. It's Wednesday, November 12th, and we are walking through EM-3, the POGIL on energy transfers in living organisms. Okay, so did we get a chance to go through part one? I know you did. I don't think we talked about it, though. Correct? So in the first model, if we take a look at the first model, what's the units of measurement being used? Grams, G for grams. Right? So since we're measuring in grams, are we talking about energy or matter? Talking about matter. Grams is the way to measure matter. So this particular diagram, we're looking at the matter that's going in and out of the organism. So we've got an herbivore, we've got herbivore A, and it is showing us that it took in how much matter, how much grass matter did this organism take in? So if we look right here at the diagram, grass ingested, we took in 4 grams. Right? So 4 grams was ingested. Of that, or it's not going to cooperate. Seriously. The 1 second as I try to get this thing to cooperate. So I want to lose the diagram. So let's say, how much did the herbivore grow? How much growth do we have here? Someone besides Aiden here. You guys all have the answers? Yes. 0.64. Growth is 0.64 grams. And we refer to growth as, what's the biological term they're using for growth here? Biomass. Right? Biomass is the amount of mass you put on your body based on the food you eat. So that becomes our biomass. Okay, so 0.64 grams, and this is going to be biomass. What's egested waste? Which is in the next question. Egested. What does that mean? Come on, give me something besides Aiden. Egested waste, what is it? Right? Poop. Right? It's the feces, the waste product that you release. It's the poop, is the egested waste. And we've got about 2.4 grams of that. Over half of it is just pooped back out, which happens. I mean, when you eat something, there is always at least a small portion of what you eat that does not end up getting used. Either your body doesn't have a way to digest it, or your body wasn't able to get to it fast enough before you excreted it. But there's always a certain amount of the food that does not get properly digested or cannot be digested. For example, we have a hard time digesting plant material. All right. So this particular organism took in 4 grams, basically released 2.4 of the grams back out as a waste product, used 0.64 grams to build its body. And so in question 5, they're asking, is all the mass accounted for? Is all the mass accounted for? This thing was working this morning. It's not working now. So how much mass did we start with? 4 grams. How much went into biomass? 0.64 grams. Are we adding or going to subtract that? We're going to subtract because it's getting used. And same with the waste products, 2.4 grams of waste products. We're going to subtract that because that's getting used. So if we take 4 minus 0.64 minus 2.4, do we get 0? No. We get 0.96 grams if you do the math. In other words, there's 0.96 grams unaccounted for, 0.96 grams that are not getting used by this organism. That can't be. Law of conservation of matter says matter is neither created nor destroyed, but you can change it simply from one form to another. So if you put in 4 grams, you got to get back out 4 grams. Okay? So we've got to account for this 0.96 grams. Where is that 0.96 grams? So if we go to the next page, boy, oh boy. Sorry for those on the screen trying to watch this. Smartboard is not going well. And for those in class. So in addition to growth and waste, what else do you have to do with your food? What else do we have to get out of our food? We got to get energy. We have to get energy out of our food. And that's where that other 0.96 is going to be. It's in the energy that we're going to produce. Okay. So we have to make energy. What's the process we use to make energy? Through cellular respiration. Right? Cell respiration is the process that we use to produce energy. It's the process by which we can take our food and we convert it into energy. The process by which we take our food and we convert it into energy. All right. So it says, as we go through cell respiration, what products do we make? So based on the other hours, it does not sound like you've got a lot of background on cell respiration anymore. So let's just we'll give you the real basics right this moment. We'll get into details later in the course. So cell respiration, you're breaking down your food. Most of your food is what you see on the food label: proteins, carbohydrates, and fats. That's mainly what you're eating. Which one do we primarily use for energy? Carbohydrates, usually sugars. You might know the sugar we most often use. Glucose is the sugar we most often use. So in respiration, we're taking glucose. To that, we are breathing in what? Oxygen. This is why we breathe in the first place, is so we can do this process. We take in oxygen. Right? That's not the answer to the question, but that's what we start with: glucose and oxygen. As a result, we're going to break the sugar apart and put the energy into a new form. Sugar is a big, huge amount of energy. Sugar is a big, huge amount of energy. If you want to use the analogy, it's like getting a $100 bill. It's a good chunk of money. Right? It's too big. It's not easy to spend. If you're thirsty and you want to get something out of the vending machine, you're not going to stick a $100 bill in. It's not, can be a number of places that won't even take a $100 bill. So we got to break this into smaller units. So what we're going to do is we're going to break glucose apart, break the bonds in the glucose, and we're going to use the energy to make another energy molecule called ATP. I'm not going to get into explaining ATP right now. We will do that later in the course. But understand, for right now, ATP is just a smaller unit of energy. It's a smaller chemical form of energy. If I use my analogy, if glucose is like a $100 bill, think of ATP like a dollar bill. It's just a smaller unit of energy. It's easier to spend. All right. So in respiration, we convert glucose into ATP, and then there's a few other waste products. If we're taking in oxygen, what are we giving back out? CO2. Giving out CO2. And your breath also has moisture in it, so we're also giving out water. This is really the answer we're looking for number 6. That the products we produce are carbon dioxide, water, and ATP. So then it's saying go back to model 1 and add this to the drawing. So if I go back, I need to add this to the drawing. Doesn't necessarily matter where you put it. It just has to be coming out. The arrow needs to be pointing out. We will label that respiration. And we know from the calculation at the bottom of the page that that was 0.96 grams. So now we have a balanced situation. We got 4 going in, and if I take 0.96 plus 0.64 plus 2.4, I have the same amount coming back out. Did I say 9? There's 4 going in, and if I add these 3 up, there's 4 coming out. So now it's 4 and 4. All matters accounted for. That's a balanced system. Making any sense? With me? Okay. So then we're going to go to model 2. Model 2 is adding a second herbivore. So herbivore A is the same one we saw in model 1. And then herbivore B is the new one. Again, I'm having a small problem with this. Go. So based on these 2 models, take a moment and try to answer questions 8 and 9. Try to answer questions 8 and 9 here for just a moment. Based on those 2 models, 8 and 9. Those of you watching the video, please do the same thing. Okay, so I might be jumping in a little quick for a few of you, but we'll take a look here. So if we look at the first one, what's the units we're using this time? Calories or kilocalories. Kilocalories just means 1,000 calories. So kilocalories are calories. It's a unit of measuring what? Energy. So this time we're looking at a diagram that involves energy instead of matter. So now we've still got the same rule. It's just now the law of conservation of energy. Energy is neither created nor destroyed, but simply changes from one form to another. Then it asks, what is the energy value of the grass eaten by herbivore A? So A is eating how much? A is eating 0.8 kilograms. And B is eating 5 kilograms. Which one's eating more? B. B's eating more. B's eating 5 versus 0.8. So which one's probably the bigger organism? B. B's a larger organism because it's consuming more calories. Therefore, we're assuming it has greater energy needs. So it would make sense that B is probably a larger herbivore compared to A. Maybe B is more like a deer and A is more like a rabbit. I'm not saying that's exactly what it is, but it might be some comparison like that. So moving forward, I'm going to stick to the picture here, so because I want to use the diagrams, but we're going to move forward using the questions in the packet. And we're going to get into some calculations, but again, don't get too hung up on the math. Try to understand the main ideas. So if we go to question 10, it says, what are 3 ways that the energy, basically, what are the 3 ways that energy is being used? How are we using energy in these 2 diagrams? We are using energy to carry out respiration. We are using energy to create heat. And we are losing energy to waste. Different color. So some of the energy gets released in waste products. Some of the energy is lost as heat. Some of the energy is invested in respiration to drive the reactions in our body. So then it says for each herbivore, this is number 11, for each herbivore, calculate the total energy output. Well, total energy output, we simply got to add these three together. So we get the output, I've sort of covered that up, I can't even see it. I've got 0.192 plus 0.228 plus 0.33. And if I add those up, I believe that comes out to 0.75. I'm just going to check myself real quickly. I'm pretty sure that's what it comes out to. Yes, 0.75. Okay, 0.75. So 0.75 units of energy is being released. Is that all the energy? No, because we started with 0.8. We started with 0.8. We're only getting 0.75, so there's still 0.05 unaccounted for. There's still 0.05 unaccounted for. Right? But this would be the answer to 11A, it'd be 0.75. Same idea for B, just add up these numbers. 1.6 plus 1.4 plus 1.25. If I add that up, that's 4.25, which is the answer for 11B. Right? Am I using 100% of the energy? Again, no, because there was 5. And so 5 subtract 4.25 is 0.75. So where is that 0.05 and where is that 0.75? Where is that energy going to? Which is what question 12 is getting to. Right? Does the total amount of energy output for each herbivore add up to the total amount of energy eaten by each herbivore? No, it doesn't. Right? In herbivore A, we're 0.05 kilocalories short, and in organism B, we're 0.75 kilocalories short. So where is that other energy going? What's not on this chart that should be? Respiration. No, we got respiration. Where else do we have to invest energy? What else is our body doing? Some of it's going to waste. Some of it's going to release this heat. Some of it's being used to run our bodies through respiration. What's the other thing we did with the matter? You take in food. Take in food. Partly what you do with the food is what? Digest it, yeah, but what's missing from the previous diagram? What's that? I'll make energy is respiration. So good. Thank you, biomass. Some of the other energy has to go into building the biomass. If you're going to build biomass, you have to take atoms from your food and build them into new body tissue. That means you have to make chemical bonds. You have to make new chemical bonds. When you make new chemical bonds, that requires energy. So you have to put energy in to build biomass. You cannot build biomass if you don't invest energy. You're not going anywhere there. Yes, no? Yeah. You're the most unresponsive group of people I've seen in forever. Holy cow. Somebody ever give you like drugs before you came in or what? Yeah. All right. You're not usually this unresponsive. I know it's a small group, it makes it awkward.
All the people who answer questions are here.
Oh, that's good. There's a good chance for you to step in.
Well, yeah.
When you eat something, say you ate a piece of chicken last night, your body has by now probably broken that chicken muscle, because basically you ate the muscle of the chicken, which is basically protein. So your body by now has taken that muscle from the chicken and broke it back into what we call amino acids. And so what your body's going to do sometime today is take those amino acids you got from the chicken, and you're going to create some type of human protein. You might create human muscle, you might create human skin, you might create human hair, there's lots of things you could build with it. Am I going anywhere? But it takes energy to do that. You have to have energy to make that happen. So long story short, for question 13A, you have to have it for biomass increase. To increase the biomass, you have to have energy. And then they want you to add that to the diagrams. So part of what's coming off here has to be invested back in to biomass. And as we calculated, that's going to be 0.05. So I'm going to take some of this off. So we're going to have 0.05 kilocalories of biomass. Same thing here. We're going to have biomass, only we calculated 0.75. I'm going to make some space so I have it for our next step. So now, just like the previous example, if I add up 0.192, 0.228, 0.05, and 0.33, I'm going to get 0.8. It's going to equal. Energy going in, energy going out equal. Here, if I add up 1.6, 1.4, 0.75, 1.25, I'm going to get 5. It's going to balance out. So if nothing else, despite all the numbers here, if nothing else, understand that main idea. Whether you're talking about matter in grams or you're talking about energy in kilocalories, what you put in has to equal what comes back out. They have to equal. That's following the laws of nature. Moving to where it says read this on the next page, or in the middle of that page, I'm sorry. It says biologists often refer to organic matter by the potential energy that is released when the substance undergoes a chemical change to make carbon dioxide and water. This could occur by burning the organic matter or by an organism using the organic matter in cell respiration. They're the same process. When you burn a log in a fire pit, it's the same thing your body's doing with sugar in your body. The difference is when you burn it, it's happening very, very, very quickly. And lots of energy being released very rapidly, and that's creating very huge amounts of heat release, which is what creates the fire. Obviously, you can't do that in your cells. Your stomach's not a big furnace. You don't just eat and drop food in and poof, it incinerates. Too much energy too quick, you kill the cells. So cell respiration and burning are equivalent processes. The difference is burning's too fast, too much energy too quick. Instead, we go through respiration, which breaks down the sugars little by little by little by little, so the energy is controlled. It's like your car. Your car's got a tank full of gas. You didn't go get in the car this morning and turn the key and have the entire gas tank ignite at once, because you probably wouldn't be sitting here. Right? Instead, your car has something called a fuel pump. And the fuel pump pumps small amounts of gasoline a little bit at a time so that the engine can burn it slowly and control. That's sort of like what respiration does in your body. You break the sugar apart atom by atom by atom and release the sugar very slow and very controlled in the process. So 14, how much potential energy is there for herbivore A? Well, it's right there, 0.8. It's 0.8 kilocalories of potential energy. We know from the previous diagram that's 4 grams, and that 4 grams was equal to about 0.8 kilocalories. How much goes into respiration? Again, we're just reading the chart. Respiration was 0.192. So that would be the answer for number 15. So then 16, we're getting into a calculation. 16 is saying how much of the energy is not being used? How much of the energy is being lost? So of the 4 processes, which ones are losing energy? Do you lose energy from respiration? No, you're actually creating energy in respiration. So that's a good one. That's good. Do we lose energy from heat loss? Yes, we do lose energy from heat loss. So that's one we're going to include. Do we lose energy when we build biomass? No, because you're investing that energy into building your own molecules. So the energy is still in the biomass. The energy is in the molecule. The energy is in the bonds of the biomass you build. So the energy is still present. And of course, if you release waste products, you're losing the energy. So the two that I starred, those are the two things we do to keep energy in our bodies. And the two that I put check marks by, those are the two ways that we lose energy. So the question is, what percent do we lose? So to get the percent we lose, you're going to take the amount that is lost as heat, which is 0.228. Let me make a little bit of room here. 0.228. And we're going to take the amount we lose as waste product, which is going to be 0.33. We're going to divide that by the total, which is 0.8, and multiply the whole thing by 100. So I'm just taking the total energy loss due to heat loss and waste removal and dividing it by the total to get the percent. And if I work the math out, that comes out to about 70%. This guy is losing 70% of the energy in his food, which, remember, is what we talked about with the pyramid. About 70% gets lost. If we go over, so that's the calculation they're looking for in number 16. For number 17, they're telling you to do the same thing for B. So again, B, we're looking at heat loss, 1.4. We're looking at waste product, 1.25. Divided by the total, which is 5, multiplied by 100. If you pop that in your calculator and figure it out, it would come out to 53%. So herbivore A is losing 70% of the energy that is in its food. Herbivore B is losing 53% of the energy that's in its food. Which, another way to state that, how much energy is herbivore A using? 30%. So if I'm losing 70%, that means I'm using 30%. And over here, if I'm losing 53, I'm using 47. So what question 18 is getting at is which one's more efficient? Which one's getting more energy out of its processes? B. A only gets 30% of the energy. B gets 47% of its energy. So B is quite a bit more efficient than A. B is doing something that's more efficient, has some type of abilities to acquire its food and process its food a little bit more efficiently than A does. So A, 70% of what it takes in doesn't do anything, only 30% actually gives it anything, compared to B, where 53% doesn't really do much, but 47% is used. So B would be considered the more efficient organism in this case, which has an impact down the road, which we go to the last page. Has an impact down the road when we start talking about carnivores and things that eat herbivores. Right? So when you have a carnivore, what part of the organism does the carnivore get to use? The biomass. Whoops, I'm going to take that away. So when a carnivore eats you, he doesn't get the waste product, he doesn't get the heat, he doesn't get the respiration. What the carnivore gets when it eats you is your biomass, your energy that's stored in your barns. Your stored energy is in your biomass. So when the carnivore eats one of these herbivores, that's where the energy is. So the next two calculations are saying, okay, what percent of the energy goes to the carnivore? What percent of the energy gets to go to the carnivore? So if I eat this guy, if I eat organism A, right, if I eat organism A, how much is in the biomass? 0.05. Yes or no? So there's 0.05, that's how much kilocalories are available out of the original 0.08. And then if I multiply that by 100, I can put that into a percent, which comes out to 6.25%. If I'm a carnivore, say I'm a wolf or a coyote or something, and I eat this herbivore, I'm going to get about 6.25% of the energy that originally came from the grass. On average, what again should I get? About how much energy passes each level? Food pyramid, energy pyramid, how much goes up? 10%. So on average, it's 10%. In this case, it's below average. I'm getting 6.25%. Yes or no? So of the energy of this original 0.8 that was in the grass, the carnivore gets only 6.25% of that. Same idea over here. We had 0.75 kilocalories is how much we get from biomass, divided by the original 5 kilocalories times 100. That comes out to 15%. So if I eat organism B, I get a little more than 10%. I get 15% of the energy. So if you're a carnivore, which one's going to give you the more bang for your buck? B. B is going to give you 15% of the original energy, where A is only going to give me 6.25% of the original energy. I'm going to get more than double the energy if I eat B. So mathematically, we're showing you the different ways that energy can be transferred. Bigger picture. The takeaways, what I want you to understand. Right? Bigger takeaways, bigger understandings. When you look at matter or you look at energy, what goes in has to equal what comes back out. If you put in 10, you got to get out 10. If you put in 100, you got to get out 100. Things just don't magically show up or disappear. Everything has to be accounted for. Another takeaway is not all organisms require the same amount of energy, and not all organisms have the same efficiencies. Some organisms, particularly bigger organisms, typically require more energy than smaller organisms. And some organisms are better adapted for their environments and therefore more efficiently use their energy. They get more than 10% of the energy passed on. And some organisms are not as well adapted or not as efficient, and they get less than 10%. But on average, about 10% goes up each trophic level. So on the test quiz, I'm not so worried about you being able to do a calculation with the formula. Just being able to interpret what those numbers mean is more important. Any questions? Yes. In the last one, herbivore B was 15%. For those that have been watching the video today, the band is down in Detroit filming. We've been getting hit with a number of students getting quarantined. There's about 8 of us here in class today. So if it sounds quiet, that's why. Okay. While that may not be the smoothest video, hopefully for those that were not in class, that gives you enough information to be able to complete the activity. Please complete the activity and submit through Google Classroom. Thank you.